So, this is the way we solve the ignition of a thermally thick solid, where the conduction inside solids is very important. Now, some typical solutions we will provide, basically considering some approximations. So, the approximate solution to the thermally thick solid for a particular case where a high heat flux is provided and the heat loss is negligible. Under this condition where heat flux is high enough, not bare minimum heat flux. See, as I told you, there is a critical heat flux or minimum heat flux which will try to heat up the surface. So, what happens if you go below that, the surface will not be heated up. The heat coming in will not be able to compensate for the heat loss. But when you have a bare minimum heat or a critical heat flux, then you will see that there is a growth in the surface temperature. I am not talking about that, I am talking about much higher heat flux now, much higher heat flux, so that the heat loss term can be easily neglected. Under that condition, this is very high. For thermally thick solid, I have a solution for the ignition time or time for ignition, which is nothing but pi by 4 k rho c T ignition minus T infinity square divided by the incident heat flux square. So, now this is nothing but thermal inertia. A product of thermal conductivity, density and specific heat of the solid is the thermal inertia. Now, ignition temperature, this is the ambient temperature and this is the initial the heat flux, the incident heat flux. Now, clearly when the incident heat flux increases, you can see that the time for ignition decreases. So, it actually decreases in a non-linear manner. And if the ignition temperature is higher, this may be ambient temperature which is lower, which this temperature difference increases, then time for ignition obviously will increase for a given heat flux. Now, thermal inertia, properties of the solid itself, if this increases, thermal inertia increases, then also the time for ignition will increase. So, if you want to, so there are multiple components. See, T ignition itself is a property of the material, correct? For a particular material, there is a particular pyrolysis temperature or ignition temperature at which enough volatiles are released and ignition is sustained. That means, the material properties itself, K rho C, which I group it as thermal inertia, or the T ignition will be able to affect the ignition time. Basically, if they increase, the ignition time will increase. The external component, the incident heat flux, the external heat source, which is trying to heat up the component now, that is in the denominator. If it decreases, then you will see that the ignition time decreases. Obviously, we are talking about a situation where the incident heat flux is much higher than the bare minimum or critical heat flux, so that the heat loss is now not taken into account. Okay. And the pyrolysis ignition temperature is a parameter of the material, and K rho C also is a parameter of the material. Now, I group the ignition temperature and the K rho C to form another parameter which I already discussed in the first module called thermal response parameter, which is the single parameter grouping the thermal inertia and the ignition temperature like this: TRP equal to T ignition minus T infinity into under root pi by 4 K rho C. Now, with this definition of thermal response parameter, I can write the ignition time for a thermally thick solid where the Q incident is much more than the critical heat flux, which will just cause temperature rise in the solid, as T ignition equal to TRP square by QI square. That is it. So, ignition of solid is dependent on TRP. So, for material I do FPA test or lift test etc. to determine TRP. How I determine TRP? I first determine K rho C and T ignition, from that I determine TRP. If I list that, then for a given incident heat flux, I can find what is the ignition time, because TRP is known to me now. Do you understand? So, that is the main thing what we do. But normally, why we are considering a special case of high heat flux? Because the ignition occurs only when the heat flux exceeds the critical heat flux, and there is no point in going for cases where the ignition will occur at a very long time and so on. We are talking about the accidental scenarios where ignition definitely will occur. Under the condition, you will see that the critical heat flux should be met, and we are talking about the case where the ignition is sure to happen. So, the incident heat flux is much higher than the critical heat flux. So, under this scenario, the ignition time can be very easily found by determining the thermal response parameter using the experiments like FPA, lift, etc., and the value of the incident heat flux itself. And one more thing is, if the flame forms over the solid surface, the heat given back by the flame to the surface will be normally very much higher than the critical heat flux itself. Now, let us analyze the thermally thin case. Okay, now let us consider solid which is heated in two configurations. In one, it has a physical thickness Tp and heated from one side like shown here. So, this is a solid surface of thickness Tp, and it is heated with a given value of incident heat flux from one side. The other side, the black line can be insulated. This is one scenario. The second scenario, there is a solid again of thickness 2 times the Tp, but it is now heated from both the sides of same heat flux. Okay. Now, this is the scenario we are considering. When the ignition occurs, etc., we will, so time to ignition we are going to do. But in this scenario, we are now considering the Tp such that for the given heat flux, it will be thermally thin. Correct. So, just because I choose a Tp value, I cannot determine that as a thermally thick or thermally thin. In combination with the heat flux alone, I can do that. Okay, now, the energy storage capacity of the material, what is that? It will be rho C into Tp. It is, see, it is like the energy density per unit temperature, that is joule per meter cube Kelvin. That is the unit of the energy storage capacity. Any storage capacity, etc., volumetric terms basically. Density, when you talk of energy density or say density itself is a volumetric term, correct. So, per unit volume, what is the energy it can store per rise in the temperature. So, that is the energy storage capacity basically. Now, this is rho C Tp. Now, for a thermally thin solid, the heat conduction within the solid is neglected. So, I have now chosen the value of Tp and Qi double dash such that I can qualify this configurations as thermally thin configuration. Okay. Now, what I am saying is there is incident and there is a heat loss also which is happening here. A generic condition I am taking. So, Q dot double dash, it is the heat flux which is lost. So, the net heat flux will be the incident heat flux minus the lost heat flux. So, the rate of rise of temperature will be equal to the energy storage capacity rho C Tp into T minus T infinity. Basically, this T can come here. So, this is like just like what? Rho C dou T by dou T. That term I am like trying to write in this different way. Basically, this Tp will go to other side. Do you understand? So, the same governing equation only I am now taking, but please see that instead of the conduction term, I am now giving a term here which is like a heat transfer term straight away. The rate of, so this is what I am trying to say is this is transfer, this rise in temperature is due to some heat transfer which is given by some flux, that is it, into say this flux per unit meter. That is what I am trying to say L I will say or Tp. This is what I am trying to write here. So, this term basically is written as rho C Tp delta T. This is the time. So, now I am talking about a time T at which the temperature of the solid surface is capital T. Now, when I say temperature of solid surface, because of the fact that this is a thermally thin material, the temperature inside the solid also will be approximately T, okay, because the heat transfer within the solid is much faster in the thermally thin case. So, we can say T is the temperature at time T, okay. So, that is this heat temperature rise is caused by the net heat flux which is coming in. So, this is the balance heat equation for the thermally thin solid where I do not have the conduction term K into d square T by dx square. So, now, so let us analyze this. Heat loss from the surface will basically be very less initially when the solid sample and the ambient temperature are the same, it is 0. When the surface temperature increases, there will be some heat loss and it will grow. The heat loss will increase as the surface temperature increases. Now, the incident heat flux should take care of the resulting heating. If the incident heat flux is not able to cause a positive net heat transfer to the solid, then the solid will not be heated up. Okay, so that is what the situation clear here, given here. This is the time, the temperature versus time curve. Let us take, this is the one incident heat flux value, say 1, this is 2, when I say critical, and this is very high, 3. Okay, 2 and critical are the same, critical heat flux. Now, when it is low heat flux, less than the critical heat flux, temperature from the initial value increases and attains a constant value. This is the ignition temperature, it will not even reach the ignition temperature. Now, I calculate the heat loss, etc. See, please understand that heat loss term is not a constant term here, because of the fact that it depends on the surface temperature, it has to grow slowly. This will also increase slowly. So, what I am trying to plot here is the increase in temperature as a consequence of the difference between the incident heat flux and the heat loss. Incident heat flux is constant, but the heat loss term is growing now. So, that this difference actually now becomes higher, smaller basically, correct. So, that is the fact that here in this case it is not able to reach, it is increasing to some level, but it is only reaching a temperature which is less than the ignition temperature or pyrolysis temperature. Now, when I increase the heat flux, incident heat flux to critical value, then it somewhat reaches the ignition temperature. Okay, now, what it is? Again, it will produce more flashes and finally it may ignite very slowly as the temperature asymptotically reaches the, see, it is asymptotically reaching the ignition temperature. But where ignition is sure to occur? When there is a high heat flux like this, where the heat loss is always compensated by the heat flux and temperature rises like this, and it goes beyond this. After even reaching the pyrolysis temperature, the growth in temperature is there, and this means that we are going to definitely have the ignition. So, in this situation, this is the temperature profile. Okay. Now, please understand that the approximate solution can be obtained when the heat flux is taken as a constant. Now, how will I do this? Now, I have to assume some surface temperature and do this constant heat loss calculation, correct. So, initially the heat loss will be 0. After it, say for example, I need some surface temperature, I will assume some surface temperature for which some heat loss will be there. So, from that I can take a heat loss parameter, or else I have to numerically solve it, that is it. So, upon this approximation I get the equation like this. Now, I know this value of heat loss parameter which is variable, but now I have calculated at the average surface temperature, okay. So, now I get the temperature profile like this, from which I can get back the ignition time as the rho c Tp temperature difference divided by the, this is nothing but the net heat which is time, this is positive. As far as the solid is concerned, this is the positive heat transfer it receives. So, this is the time, I can calculate this time. Again please see this, this is this net heat flux and Tp are chosen such that the solid is already classified as thermally thin solid, and I can get the ignition time like this. And as I told you, the ignition time is the only important parameter for a solid to burn, correct, because the pyrolysis time, we have already seen that the pyrolysis time, or the when the pyrolysis occurs, then ignition automatically occurs. Pyrolysis time is of order of 100 seconds. The mixing time is order of 1 second or 10 seconds, but the chemical time is order of 10 power minus 4 seconds. So, that means that this is the complete rate controlling parameter for us. So, we are talking about the high heat flux cases where definitely ignition will occur, and based upon the high heat flux case, we have got the expression for the time for ignition for thermally thick solid as well as for the thermally thin solid. In the thermally thick solid, obviously we need to solve for the heat conduction within the solid, but in the thermally thin we need not do that. Now, some factors which are affecting the ignition for the thermally thin. So, we have classified Tp value based upon the conductivity, heat flux etc., and classified that as thermally thin. We can also do the thermally thin criteria by using the non-dimensional number called Bio number, which is nothing but H, the heat transfer coefficient, Tp, the physical thickness, divided by the K, the thermal conductivity of the solid. So, H Tp by K is the Bio number. Understand that this is the thermal conductivity of the solid. Now, if the Bio number calculated in this manner, so now how will you calculate H? H is, see for example, given some heat flux, based upon the ambient temperature and the surface temperature, if I take some average value of H, that you plug in here, Tp is known, K also is known, then calculate Bio number. If Bio number is less than 0.1, then the conductive resistance is very small, so that the surface temperature can be assumed as the internal temperature also. So, we can say the material is thermally thin. Okay. So, if you say if the material is about 1 mm thickness, then most practical applications where the heat flux are going to exceed say 20 kilowatt per meter square, the thermally thin assumption can be made. Otherwise, we have to invoke the thermally thick. So, 1 mm thickness we will not use for practical applications. So, that is what in most of the practical applications we have to consider the thermal thickness into account. That is, the physical thickness will be such that it will be thermally also thick. Now, solution for the ignition to the thermally thin material does not include the conduction. We have already seen that. Similarly, the fuel degradation or the fuel exhaustion, that is the fuel being consumed. See for example, if there is a thin plastic layer, when it ignites basically here, it also burns. That means when it burns, the component of the fuel will not be even present there. So, that is, there is no need to consider the solid phase at all when you classify the material as thermally thin. if the material is so thin, okay, there are some other aspects which we need to understand. So let us take a very thin material where you are exposing to heat fluxes of very high values, 50 kilowatt per meter square. Then what happens is, it may not ignite, it may just decompose and produce smoke or char, etc., based upon whether it is a charring material or not, and will not even ignite, that is all. It will just vanish by decomposing, because of the fact that when you have a very thin material, when you subject to very high heat flux, what happens is, some vapors, some gases will come out of this, but these gases mixing with the air from the ambient may not produce enough volume of the premixed reactant which can ignite. That means it will just decompose. When the volatiles come out, etc., it will just decompose and leave char, or nothing will be there. So, it will just decompose. So, the enough pyrolusate or volatiles will not be coming out of this thin material and feed the and form a volume, enough volume of the mixture to get ignited. In this case, we will not see any flame, only it will just decompose, and if it is charring material, char will be left behind. Okay. So, these are the aspects which we will consider about a thin material, thermally thin material. Okay. So, thermally thick, it is not the case. Thermally thick means already when you have higher ion and higher heat flux, in-depth conduction also will be occurring at a higher rate. So, more volatile or the gases will come out, and now you can see a flaming combustion for sure. So, thermally thick material, your incident heat flux is increased to higher and higher value, this rate of conduction also will increase inside, and that means that the heat up will be faster, more volatiles will be released, and it will sustain a flaming combustion. Thin material, it is not so. So, the burning of say curtain layers or cellulose sheets, etc., will be very complex because of the fact that they are transient in nature. In this case, a steady burning can occur in the thick case. The thin case, it is not, it is only transient, it is very highly time dependent. Okay. So, there are differences between thermally thick and thermally thin cases. Okay. So, the next aspect is the fire spread. So, as we have already seen, once we have a solid fuel, somehow I ignite it. First of all, I need to heat up, get the temperature, surface temperature to pyrolysis temperature or ignition temperature, then form a flame. Nice. Now, this flame has to propagate. So, sustained flame is formed. So, ignition is over now. This flame has to spread over the solid material. For that, it has to heat. The flame has to heat the layer of material next to the anchoring point and produce more volatile gases, and this volatile gas is mixed with the ambient air and form a mixture, and the flame passes over this. So, this means that the heat feedback from the flame to the surface is extremely important for the flame to move, or we can say that this is one ignition is occurring due to external heat flux and also the final flame. Now, the subsequent ignition is caused by the flame itself. Do you understand? So, the flame spread, as I told earlier, is a subsequent ignition process of the downstream layer of the fuel, and causing the fuel gases to come out of the condensed surface and mix with the ambient air, and flame will propagate through that. Okay. So, a moving flame in close proximity of the source, where the fuel vapor or gas originating from the condensed phase will be able to feed the flame from the fuel side, ambient air from the gas side can come and at least sustain the diffusion flame. That is the flame spread process here. So, the fuel gas or vapor originating because of the pyrolysis or vaporization, okay, depends on heat transfer. As opposed to liquid fuel, the solid fuel flame spread is heat transfer controlled mostly. The liquid fuel, on the other hand, the surface would have already reached the fire point. Now the flame spread, basically what happens is, if the temperature, initial temperature of the liquid is more than the flash point temperature, then the flame spread will be basically a premixed gas type of flame spread, very simple. But in the case of solid, it is not so. The flame has to heat up the subsequent layers and move downstream. Okay, so that is one of the important difference between the liquid and this. But even in the case of liquid, if you have a sub flash point initial temperature, we have seen that regimes are observed, pulsating regimes, non-uniform flame spread, then the pseudo-uniform flame spread, then uniform flame spread where the flame spread rate increases, then finally asymptotic value of flame spread rate we have all seen. So in this case, basically we have more complex phenomena occurring in the solid phase. So we have to see that. So now this particular photograph here shows the flame over a flame spreading over a 2.5 mm thick PMMA slab, okay, polymer slab. There is a airflow velocity, so of about u infinity is 0.8 meter per second. Now please see this, the flame anchors at this point and the fuel layer is like this. From this point, the flame is anchored here, the air velocity is in this direction. So this line indicates that the flame is anchored at that particular location, and there is a fuel surface to the left of this line and a long fuel surface to the right of this line also. Now what happens is, if there is a uniform velocity coming in this direction, then this point the flame will move in the concurrent direction, in the same direction of the air velocity, or in the opposed direction opposing the air velocity also, because there are fuel layers which is available. See, for example, I take a long PMA slab and ignite at the middle, and from left to right there is a airflow. So from the middle to the right side I will have a concurrent flame spread, from the middle to the left side I have a opposed flame spread. So in one shot I can see the behavior of both concurrent and opposed flame spread. So important parameters in this case is, first of all we will see pyrolysis length. What is the length of the fuel surface which is heated by the flame? That is the pyrolysis length, causing pyrolysate or the volatiles to be released. Okay, this is the length which has been heated by the flame, causing volatile release already. Now next one is called heating length, LH, or heated length, which is the length to which the flame has heated the fuel but pyrolysis has not occurred yet. Okay, so we will continue in the next class with this configuration. The flame process in a solid is complicated than that of the liquid because of several factors which we will see subsequently. So I will stop here.